Triangular wedge is fixed to a horizontal surface. This wedge isn't moving. If it was, that would be a lot more complicated, but it's just fixed here on some surface. Cool. And on it, we have this sort of pulley system on top of it. Right, so this will probably look familiar if you're doing these kinds of questions. They've drawn the diagram for us, which is really nice. They didn't have to do that, but they have. So we can just start using this and marking on some forces. The first one I'm going to mark on is the force acting down the slope here, which is mg sine alpha. Coming from mg here. This was mg. But I'm going to leave that out of this diagram. There's no real need to draw that in. And then there's going to be an mg cos alpha here. Okay, let me talk a bit about why that is so. So how did I spot to do that? Quickly, well, is a really badly drawn slope. Just using the general fact that if I have a mass mg acting, there's always going to be a component of weight parallel down the slope of angle of magnitude mg sine alpha, right? That's a fact you should know, a basic mechanical fact you should just be happy with. And how do I remember? Some people get mixed up between what is this sine or cos. Well, you can remember it's sine because the S sort of stands for slide. That's how I do it. And if I resolved it, if I wanted to find the component this way, it's obviously mg cos alpha. When I had that other side of the slope here, it's the same kind of scenario, except this angle was pi over 2 minus alpha. And my guy here was, the force acting down was, again, it was like mg, and then it would be sine of pi over 2 minus alpha. But we know from a trigonometric identity that's equal to cos alpha. Okay, so a little bit of a side tangent here. That's just an identity you should be aware of, right? So if you're not aware of these two, they can be incredibly useful in mechanics problems. Okay, so sine of 90 minus an angle is just cos of that angle, and cos of 90 minus an angle is just sine of that angle. And if you're a bit confused as to why this is so, well, imagine we just have our old SOHCAHTOA situation here, where we have some angle alpha, and then you have the opposite side, the hypotenuse, and the adjacent. We know that cos of alpha, for example, that's a over h. Now this angle is obviously 90 minus alpha, pi over 2 minus alpha. And we can see that sine of pi over 2 minus alpha, just use your SOHCAHTOA rules. This time the opposite of this angle is this side, so it is indeed also a over h, so they are equal. At least this shows for angles between 0 and 90, right? So that's what I use to draw on those forces very quickly. Well, once you're done that, you just need to read here, the contact surfaces between the boxes are smooth, so there's no friction, so that's quite nice. It means you can do this question pretty quickly, right? We have some tension acting up here and some tension acting up here, but there's no, the only other force I'm leaving out, I guess, are the forces going this way. We know that there's like a reaction force and the component of weight acting this way, but they are relevant in this question. The things we know about the tension are that the tension is equal to mg sine alpha, and we also know the tension is equal to mg cos alpha if the system's in equilibrium, right? So the question asked us to show that if tan alpha is greater than m over m, it will slide down this way, okay? And you should be looking at this and thinking, okay, well, what if tan alpha equals m over m? Then it's going to be in equilibrium. And if tan alpha is less than m over m, it's probably sliding the other way, right? So that's what's happening. So let me be a bit more clear about that if that sounded confusing. So if the system's in equilibrium, we know that the tension is equal to both of these two things. Both of these two things must be equal to each other. This means that mg sine alpha, which is the tension from the left box, we know that the tension is the same because it's the same string, and it must be also equal to mg cos alpha because these things aren't moving side to side. So I can just say that they're equal to each other like that. Okay, cancel the g's and divide by cos alpha, and we get this. Okay, that's where the first part comes from. That's if it's in equilibrium. And you can see that if I make alpha any bigger, from my diagram, if I made alpha any bigger, I'm just making the slope kind of steeper, and indeed things would be sliding down in that way that you expect. Okay, so that's kind of how you answer the first part. The system's in equilibrium. Left forces equal right forces in both particles. The two trigonometric terms have to equal each other, and then you just get tan alpha is m over m, right? It's not too bad. Let me show you how to do the next bit. There's a little bit of algebra here. So given that tan alpha equals 2m over m, so that means that indeed we are sliding down this way currently. We want to find a nice expression for the magnitude of the acceleration. Okay, so if I just apply F equals ma, along the pulley, the first force we have will be mg sine alpha. Then I'll have plus tension minus tension, so leave that out. And I'll have this scenario, and that must be equal to a times m plus m, kind of like that. Right? How did I do that? So I'm really saying here that this side is the force, this side is, ma, right? F equals ma. That's what I'm doing. And I'm applying that along the pulley. So I'm starting here and I'm going all the way along the string. And that's the force acting this way. The total mass of this system is the sum of the two masses. And I want to show the accelerations like this. So keep that in mind. G sine alpha over tan alpha plus 2. So I want to do that. I want to show that the acceleration is g sine alpha over tan alpha plus 2. It looks kind of weird, but it doesn't look like we're quite there yet because if I divide by the mass, I have g m sine alpha minus m. Sorry, this should be a cos. Yeah, there we go. M cos alpha over m plus m. Okay, that's what I get. It doesn't quite look like that though, does it? So we're going to have to do a little bit of algebraic manipulation here, right? So currently this is my expression, and I want to make it look like this. And I know that tan alpha equals 2m over m, and we want to apply that for the question, right? How are we going to do this? Well, what I would do next is I would look and I see, okay, so I see the g sine alpha here. I want to sort of get that in my expression here. So I can factor out sine alpha. What I have left in there will be m minus, m cos alpha over sine alpha. Over m plus m. Happy so far? All right, that's by just taking the sine alpha out. Now what's this guy here? It's cos alpha over sine alpha. That's 1 over tan. All right, so that's 1 over this guy. So cos alpha over sine alpha, that's 1 over tan, which must be equal to the reciprocal of this. So m over 2m. All right, so the green guy literally equals m over 2m. Then those m's would cancel out. And I'd have m minus m over 2. So, just to be a bit more clear, on the top line, I mean m minus m over 2. Well, that's just equal to m over 2. So that's the top line, right? So overall, what have I got? I've got g sine alpha. M over 2 in the top line. Let me just move that 2 to the bottom. a little bit more like the expression that we need now. We just want to put tan alpha back in there. So notice that this thing is tan alpha plus 2 on the bottom line. Well, you know, I would then take the hint to divide by capital M. So divide top and bottom by capital M. And what have I got? I've got 1 over 2 plus M over M. And what's M over N? Well, remember, I know that tan alpha equals 2M over M. Sorry, there should also be a 2 there. Oh, well then it's just there, isn't it? So that's tan alpha. So we have shown indeed that this is equal to G sine alpha over 2 plus tan alpha. Right, so if you look at this, what were the advantages of putting the acceleration in this format? Well, now it's just a function of alpha. It's like independent of the masses, right? So I know the acceleration is purely a function of alpha. And no matter what the masses are, I have the acceleration of the system purely in terms of the angle that I had there. That's pretty interesting. So I've sort of disregarded any information about the masses, and now we can sort of ask the question, when is this maximized? Right, like what angle can I pick here such that I'll have the most acceleration? Like, how can I make acceleration the biggest? Well, all I need to do here is simply go like this. Right, so if this is my acceleration by A, I just go di by d alpha. I set that equal to 0. Okay, so then I'm basically asking the question, okay, well, if I set the derivative of this to be 0, then that'll give me the value of alpha such that that will happen, that will be the maximum. Okay, so let's do that. Let's differentiate this with respect to alpha using the quotient rule. So get low. So low d high minus high d low, differentiate tan, I get sec squared, right? Over the square of what's below or whatever, but I'm just setting up to 0. I know that I only need to consider the numerator of the thing in the quotient rule, and then I want to set that equal to 0. And that's enough to say that the first derivative is 0, right? So let's simplify this a bit. I can cancel the g. Tan alpha times cos, that's it's going to be sine alpha, isn't it? What's the best way to do this? Well, I know that I know what tan alpha is. Tan alpha is 2m over m, so I guess the more tan alpha is the better. Yeah, I'm going to what will I do? I will I'll write tan alpha as t, right? So here I have 2 plus t times cos. All right, I'll divide by cos. So if I divide by cos, I get, you know, there's another, this is going to turn into a tan as well. Then I have a sec squared alpha. That's going to be a tan squared plus 1 using a trigonometric identity. Okay, so how did I get from here to here? I just sort of divided by cos, so the sine became a tan alpha. Right, and then I have this equation, so I'm just rewriting this. Instead of tan alpha, I'll just write t because it's a little bit faster. Notice that this will just become, so I have that equation. So that's true when the first derivative happens. Remember, tan alpha is 2m over m, so if I cube it, I get this. 2 minus that equals 0, so move the 2 to the other side, and then I can just simply say this. Okay, cool. So that's the result I think we wanted for the last part. Yeah, there it was. So the acceleration is indeed maximized at 4m cubed equals m cubed. Okay? So that's pretty much all parts of the question done. I know maybe I got a bit confusing in the middle of the explanations of that there, but there we are, right? I think there was a few tricky pieces of algebra here, but because it's sort of a show that question, you know what result you want to get towards. This guy, we were able to do that by slowly factoring more things out of the expression to make it look like what we wanted it to look like. You know, it's not exactly how to go here, but I knew that I didn't want an m on the top line, because if you look at the numerator of this expression, there's no m there, so I thought dividing by m was a good idea. There it is, you can plug tan alpha back into it. And just to be clear about this bit, this is the acceleration. We want to find when it's maximized, so anytime you get asked when is something maximized, you just want to use the quotient rule. Or not the quotient rule, sorry. Anytime when something's maximized, you want to take its derivative and set its derivative equal to 0. Strictly, we should be checking that this is a maximum, but we kind of don't need to. We kind of know, obviously, that it is going to be a maximum. But there's probably a mark for checking. Maybe you want to, I don't know, draw a graph or show that the second derivative is indeed negative. Okay. But I'm not sure. I don't think I'd bother with that. I think it's quite clear from this that it is maximum. Okay, so I hope that was helpful for explaining how to do this question.